Hello again. This is Math 2270 coming to you from the College of DuPage. And the title of this lecture is Introducing LSA 3. As always, please be attentive while watching this video. An interesting and important geometric model arises when one tries to determine the path of a pursuer chasing its prey. This path is called a curve of pursuit, and it has a lot of warfare applications, but it is interesting mathematically. These problems were analyzed using methods of calculus back in the 18th century, but Leonardo da Vinci actually thought about these problems back in the Renaissance 2 centuries before. The simplest problem, which is what we'll talk about here, there can be much more complicated problems, is to find the curve along which a vessel moves in pursuing another vessel that flees along a straight line, assuming that the speeds of the two vessels are constant. If you change these assumptions, it is a way harder problem, of course. And vessel here means, let's just think about these being ships. So here is a vessel A, and here is a vessel B. Okay, so A is pursuing vessel B. Okay, so here we go. Let's assume that vessel A, traveling at speed alpha, is pursuing vessel B, and is traveling at speed beta. In addition, assume that vessel A begins at time 0 at the origin. So you see, vessel A starts here at time t equals 0 and pursues vessel B, which begins at this point, 1, 0, and travels up the line x equal 1. After t hours, vessel A is located at a point xy. It's pursuing that. And vessel B is located at the point Q, which is going to be 1 comma beta t. This comes from distance equals rate times time. The goal is to describe the locus of points P, that is, find y, which is this pursuit curve, as a function of x. Okay, now here are some things that you're asked to do, and the steps are kind of shown out. But what you want to do is work through these things. So, part A, vessel A is pursuing vessel B, so at time t, vessel A must be headed right at vessel B. That is, the tangent line to the curve of pursuit at P must pass through the point Q. And here's a picture. So there is Q and there is P. For this to be true, I want you to show, and you have to work through this, and when you're submitting this on the answer sheet, you want to have a narrative argument for this. So you want to show that dy dx is equal to y minus tb over x minus 1. That is part A for you to do. Part B. We know the speed at which vessel A is traveling, so we know the distance it travels in time t is alpha t. Again, this is distance equals rate times time. The distance is also the length of the pursuit curve from 0, 0 to xy. Use the arc length formula from your calculus. You want to show that alpha t is equal to the integral from 0 to x. You see your variable is up here. And this is the square root of 1 plus, this is y prime at u whole squared under the square root plus 1 du. And you solve for t in that equation, and you conclude with 6 that y minus x minus 1 whole dy dt over beta equal 1 over alpha times this integral. So there's two things to do in part B. So show this and show this. Part C, differentiating both sides of 6, this is equation 6, with respect to x, derive a first order differential equation, and it's shown here, x minus 1 dw dx equals minus beta over alpha, the square root of 1 plus w squared. And this is what w is. W is dy dx. So again, you're supposed to show this is true. It goes on. Part D, using separation of variables and the initial conditions that x equals 0 and dy dx equals 0 when t equals 0. Show that, and again, this is another thing you have to show, dy dx is equal to w equals to 1/2 times 1 minus x whole to the minus beta over alpha minus 1 minus x whole to the beta over alpha. Part E, you are to assume for alpha greater than beta, that is, the pursuing vessel A travels faster than the pursuing vessel B, and you want to use the equation 7, which is this one, and these initial conditions to derive, this is the curve of the pursuit. So this is actually a solution to the problem. So show this is true by solving this equation, this initial value problem up here. Then part F, you're to find where does vessel A intercept vessel B. And we're assuming again that alpha is greater than beta. And finally, part G, you want to show another thing. Show that if alpha equal beta, they have the same speeds, rectilinear speeds. Then the curve of pursuit is given by this expression. And lastly, this could have been F, G, H. This could have been H. But another question, will vessel A ever reach vessel B? In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.